be a problem? What am I hearing from the operations team, let's say, or from the users, or whatever it might be? Why is this a problem? What is going to give me some of those telltale signs? So that's kind of my goal with this one, to play with. So one of the things we'll do is who was not here in December, at the December? Oh, a whole bunch of them. So we got about half and half, somewhere. All right, so I'm going to do a really kind of quick overview of V6, because most of it is going to be part of the focus tonight, all right? And then I will have this presentation and last month's presentation available maybe by the end of the week, and so they can get it on the website, so at least you get it. Supposedly they're recording tonight.
We are recording tonight.
Man said they're recording.
So if you have side conversations, they're being recorded, so make sure they're important.
So no other extra talking, right, as we go. So we'll do that. Same thing, I'll kind of go through a few just little quick things of Wireshark, because now I want to be really bringing them together. Again, part of my thinking in how I use Wireshark in troubleshooting generically, and especially for IPv6, because it's new to people, new to us, all right? It is not a new technology, but is to get the eyeballs focused, all right? Let's weed out the stuff that doesn't matter. That would be V4. That's the first thing, all right? If you've got V4 and V6 in your trace, get rid of your V4. Stop it. Turn it off. Yeah, that's not going to happen in our lifetimes, all right? But how can I weed through the things that don't matter and then start to focus on the things that do? And there's a couple of philosophies. First off, you got to kind of, do the let's trim it 50%. Let's get rid of V4. Okay, now what am I looking at from a perspective of what's the protocol I need to focus with? And then maybe I can start narrowing it down even more. So that's kind of my thinking. So that's why, as a little bit of a repeat of the V6 and the Wireshark, again, is because that's how we're going to be using it. We're going to move to this tool, all right? You got to look through the packets, because who's hanging over us while things are broken? Layers 8, 9, and 10, right? And all they're doing is saying, did you fix it? Did you fix it? Did you fix it? Did you fix it? And all we are as the network people have to say, it's their fault. I know it is. I just got to prove it beyond reasonable doubt, all right? Because it's never the network. I repeat that a lot. All right. So the big address, colons, 16 bits between colons, 128 bits total, and we call these hextets, each 16 bits, okay? The big thing that we need to know in the V6 addressing is that a minimal, smallest network size is a 64-bit network prefix. So that means you're going to have 64 bits of host ID on 18 billion possible addresses in that 64 bits. So everybody just starts wigging out. But if you understand this as the foundation, if you understand this again as this is the way most operating systems work, client server level operating systems, you cannot change it. This is the way most DHCP-V6 server services work. You cannot change it. And everybody says, well, that's too many addresses. I want something smaller. You cannot do it. So stop thinking it, all right? There's people on the Microsoft boards who are just screaming and yelling, oh, I want to do, 96-bit network prefixes, blah, blah, blah. You can't change the Microsoft server, all right? You just can't do some things. So if you get this part understood, a lot of your initial troubleshooting becomes easy, because I need to focus right in the middle. The left 4 hextets are network, the right 4 hextets are host ID, or more appropriately termed IID, interface ID, all right? And that kind of becomes important just from a nomenclature viewpoint, because that's the way it is referenced. We're going to call them host IDs because we're used to it. And it's a valid name, okay? But in documentation and in some references, you're going to see IID, or interface ID. So I go back and forth. But if you start thinking of it from these perspectives, even looking at the address, even using the address becomes a little bit easier in working with it. So we get all these things. The buttons doesn't work as well. The shorthand notation. This also becomes important of how you're going to see the numbers represented by different operating systems and different applications. And when I say operating systems in that kind of a term, client, server, router, firewall, blah, 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 any operating system, all right, may or may not make use of the shorthand notation. may or may not be displaying in upper or lowercase alpha. All right? Lowercase is considered the standard best practice. Using shorthand notation is considered the best practice. Using the shorthand notation in this mode here, again, we can concatenate down multiple, one or more hex text down to a double colon. What you cannot do is concatenate two groupings of zeros with double colons. You can't do double colon twice, because how many bits does each double colon represent? All right? The considered standard is I can actually even concatenate one hextet of zeros down to a double colon. It is considered best practice to not do that, but it is not illegal. All right? So we'll back up a little bit. You can also drop leading zeros. Leading zeros, now when you get into the mode of if you've done one double colon, then you still drop three leading zeros of a hextet down to a zero. Okay? So a test question on any test with V6 in it, if the question gave you these three options, it says which one of these IPv6 addresses is a valid representation, A, B, or C. Just take them A, B, or C. The answer would be D, all the above. All right? The considered best use of shorthand notation is the one that gives you the most compression. And so option 2 would be considered, or C, or the third one. The one here at the bottom would be considered the best usage of shorthand notation. It's using the most compression. All right? And those will be tricky questions in some tests. Yes, sir?
Is it favored whether, if it's equal, in that example, if it's equal, is it favored to do it on the host side or on the interface side?
Well, so the question being, is it better or more beneficial to do it on the network side or the IAD? And my interpretation is two ways. It's the RFC states they prefer more on the network, but then later on your reader says what gives you the best. And it doesn't explicitly state it must be one or the other, at least my interpretation.
I'm thinking troubleshooting, ease of
So the key of it is, there's two key points here that I'm going to bring out. One is when you're looking at it, right, the double colon, how many bits are there? The second one is, and let me see if I can write this up here real quick. There's another bit of info. So if you see an address represented, I'm going to kind of draw over here where maybe, sorry, a little bit easier. If you see an address, can't even draw. DB81:2:. So 2001: DB8:1:2:/64. Is that a network prefix representation, or could this be an interface ID's real address?
Be an address.
Network prefix, interface ID, or C, both? It can be both. The reason is 0 is a valid address. We don't have broadcast addresses in V6. It's all multicast. So 0 and all F's, kind of in V4 world, was network and broadcast. We don't have that. So that could actually be an interface's address. : with nothing hanging out. That means it's 4 hextets of zeros. And I don't have to put a 0 there. You can enter it in. Really fun. You can enter it in : 0/64, but the operating system may display it like that. So this is another just kind of a little sidebar whole thing, but you might see this in the real world on point-to-point links that are using a /127 assigned, out of a /160, or out of a /64, because ::0 and ::1 are the two bits. And it might display like this. So another little tidbit, I am not a fan personally of using ::0 because of that. I'll use /127 for point-to-point links, but I'll do ::2 and ::3, which means my 128th bit is 01. So my addresses are still actually working at 127, but I've got like what I consider real numbers hanging off, : with a number, not 01. So completely little sidebar things to deal with, and some, as early as 2 years ago, some router vendors' OSs did not allow that as a host as a host address or an interface address, : 0, because they used it as the Unicast address. So you got to be a little careful there too. So yes.
I was going to say, if you figure out the slack space by not using 0, you're not really losing anything out of the network space anyway.
Say it again now?
We remember what the big thing on IP4 was when you wanted the most efficient use of your IPs. You were trying to get the right network size, but if you went too small, you were wasting more IPs to the network and broadcast. But in IPv6, if you just want to throw away an address and not use it, what's the big deal? Yeah.
Exactly, because you guys watch. Yeah, there's no wasting in V6 world, even though it feels really wasteful to have a /64 for 200 node network. But actually what you should do is two things. One, do not address your hosts with the same 1 to 220, : 1 to 220, to match your V4 host addresses, because the bad guys are betting on that. You've just narrowed down that 18 billion and change attack space to a sand grain, right, in comparison. Use some of those other hex texts with some values to just change it up a little bit. But also, don't do :10, :1, :20, :220. Use your 4 octets in each of the hex texts to match, so it's easy, because everybody wants to do easy. Because if we're going to have to learn something, we want it to be the easiest possible way. Don't make your V6 addressing look like your V4, absolutely. The bad guys are betting on it. You've just so much narrowed down attack space, all right? Don't use words in your addresses like I've got here: 6 Lab, Foosball, Dallas. The bad guys are searching for these. It's a limited attack space. It's great for lab, but don't use it in production. And I made this statement the last time, but Facebook didn't listen to me. If you go ping facebook.com, the 5th and 6th hextets are FACEBOOC. But that's Facebook. They probably have better protection, right?
Yeah.
But again, they've already taken 32 bits of an interface ID and completely narrowed down the attack space. Now there's only 32 more bits to have to go look at. All right, but anyway, so some of the things to kind of be thinking about also as you're playing and looking at V6 and trying to deal with the addressing structure. But the shorthand notation is really interesting, and it's, I can't find any rhyme or reason. It doesn't have to be done, but the best practice is. Alpha should be in lowercase, but it's not always. One particular router vendor, yeah, those guys, displays it in uppercase, at least up through 15.0 code. I don't know anything newer than that. I don't have anything newer than that, but anyway. But it's okay. It's not illegal. It's just not everybody else does. So we have to look at those things. Oh, this would always be, the answer is no, this is not a correct representation of an IPv6 address. If you see 2 sets of double colons, no. On any test question, anybody's test, all right? And I've never found an operating system would even allow me to do this. I tried, the little hand comes out, whack, you cannot do that, all right? And that's a good thing. I'm happy for that. I don't want that kind of mistake. I mentioned this a while ago. There's no broadcast in V6 world. It's all multicast. It's either an unlinked multicast or an offlink. This is tripping us up a little bit because we're used to using the word broadcast as well for different things. Oh, we're going to do broadcast messages. We're going to do multicast. And in the V4 world, we think about multicast. No, I'm not going to do multicast. Yes, you will in V6, okay? There's reserved blocks for those addresses. So just the key there, there's no broadcast, it's an unlinked multicast. Wait a minute, I think I did not, okay. In the reserved prefix area, there's two particular prefixes that we're going to be working with a lot tonight. Actually, three, but two real primaries. FE80::, is a reserved prefix for what's called the link local address. Remember the link local? All right? That is a must. You will always have a link local address on an IPv6 enabled interface under any operating system. You will never not see it. The only way you won't see it is if IPv6 has been turned off or is not available. Okay? It will always be there. It is like the APIPA address from the V4 world, but the APIPA address goes away in V4 world. If you get a DHCP address or a static address, the APIPA goes away. All right? But in V6, you will always have this link local. You can tell it by FE80::, and then 64 bits of host ID. It's assigned out of a /10. Everything else, the other second, third, and fourth hextets are zeros. Okay? So reserved prefix. If you see FE80, link local. That means it's not routable address. It's only devices can talk to each other on that layer 2 domain. You can't route it if you wanted to. I've not found a routing operating system that would allow it. It's not supposed to. Yay, we're happy. Okay? But you will always have that one. Most likely you will have other addresses on your V6 interface out of the 2,000 something range today. Those are known as the global unicast addresses. Those are the internet route capable address blocks. All right? 2,000 to 3FFF. However, at the current basic time, we're only in the 2,000s. The only 3 range that was available and was routed was 15 years ago. They called it the 6 bone. It was the initial IPv6 backbone testing address. It was 3FFE. That has been discontinued, deprecated, turned back into IANA, doesn't exist. If you see documentation referencing IPv6 anything, and you see 3FFE, that is old stuff. It doesn't mean it's bad, it just means it's old, okay? It's just as a kind of a reference point. It's older, back in the early days of V6 kind of stuff, okay? Not anything other than that. The other block that you will see is called this unique local, and it's likened kind of, sort of, but not exactly, RC 1918. It's called the EULA, Unique Local Address Block. It is assigned out of the FC00, but FC00 is reserved by IANA. So nowadays we use FD00. Unique local means you can route it with inside your world, but not to the outside world. Providers should block it. You should too. On your V6 facing routers, your ACL should be FC::7, deny.
It's actually
You should never get them from your provider, okay? But you should block them from provider link.
It's actually a good thing to use.
Say again now?
It's a good thing to use for environments. If you're doing
Yes. I mean, it's a very valid, in your domain, you can route FC, or FDs, really, okay? Very, very valid. There are generically 2 diverse camps. Use EULA or don't use EULA. There's a few blogs out there, blog postings and other write-ups about it. I'm just going to leave it alone for now. You can use it inside. A lot of people will use it inside their world. And they may also have a global unicast to go to the outside world. So you could end up with a link local address, upwards of 4 global unicast addresses, and upwards of 4 EULA addresses for a grand total of upwards of 9 V6 addresses representing 3 different networks. Link local, the global, those 4 globals are all the same network prefix. They're just different interface IDs. We're going to see some of this coming up. The EULAs could be the same. Oh, by the way, I could now have multiple network prefixes out of global and EULA on my interface. So that limit of 9, or that number of 9, that's just the tip of the iceberg. All right? You could have more. There's a problem in this thinking of this is, how in the world, Jeff, can I have 4 addresses out of 2001 DB8:1:2:100, 101, 102, 103. 4 host IDs in the same network prefix. We can't do that in v4 world. I can multi-net. I can have different network prefixes on almost any v4 interface, on almost any operating system, but not in the same network. Not 10.10.10.1, 10.10.10.2, 10.10.10.3. You can't do that. Okay? v6 you can. So somebody asked, why would you do such a stupid thing, Jeff?
Why would you do such a stupid thing, Jeff?
Because a mistake was made. Okay? It is not always a desired result that you would have 4 global unicast addresses out of the same network. Okay? That's not a good thing. It doesn't mean things won't work. It just means you now have 4 possible addresses that you've got to do troubleshooting on, because those 4 addresses, any one of them might be used at any given time as the source IP, v6 address. Now, there are some preferences in those. We'll kind of hold off for a moment. All right? But if you had 4 global unicast addresses in the same network prefix, that is not a good thing. That means a static address was set, a DHCP-v6 address was set, and upwards of 2 automatic, what we call stateless address auto configuration, SLAC addresses have been given to that client. And that is not the way we want to operate. Okay? We'll see kind of sort of some of this in a little bit. But kind of focus on these prefixes. If you saw an IPv6 address starting with anything other really today than F or 2 or FE80, 2 almost anything, and FD, they're not valid addresses. I'm not even sure they would take. I've actually never tried to put like 5,000. It might work. I don't know. I truly just don't know. I don't see why it wouldn't necessarily, but it's not an address that IANA has assigned out yet. They've only assigned out of the 2,000 block so far. So little tidbits. Some of the other things, talking about those multicast, really the things we want to look at are 2 very specific types of multicast addresses that are basically on link. One is, do I have any routers? Remember, how does an IPv6 client not using DHCP, not using static addressing, find out about his router?
Router advertisement.
Say again?
Router advertisement.
It sends out, actually,
Request.
a router solicitation. Okay? It basically sends an all points broad, I almost said it, an all points link local multicast.
All points bulletin.
Say what?
All points bulletin.
All points not routable bulletin. Are there any v6 routers on this network? Can you hear me? All right? So they're going to send it to FFO2::2. If they are doing anything where they're testing, like, does somebody have my address? The duplicate address detection test, okay? Or I'm just trying to find some nodes, then they might send it to the FFO2::1. All right? So these are the 2 real common multicast addresses that you would see as destination addresses. All right? If you're just kind of looking to see what traffic is going on, that's a couple you could throw out there. There's others, of course, but those are, again, a couple we'll focus with tonight. A little bit on the addressing, interface IDs. There are self-assignable options. There are 2. One starts with the MAC address. This was the original spec. We got to get a unique address automatically with no human intervention, no other intervention whatsoever. So they said, well, let's start with the 48-bit MAC address to fit into a 64-bit space. there was already an existing IEEE standard known as the US64. Break it in half, pad it with FFFE, now you got a 64-bit number. V6 group said, but we want something that knows that we did it, not just simply the UE64 process. So they took an unused bit, the 7th bit of the first byte, known as the local global bit, and inverted. So by doing that, now there's a quote-unquote more unique than the UE64 process, known as the modified UE64, to create this 64-bit number that can then be appended to a network prefix, or it can be appended to the link local address, the FE80::: prefix. And now you get a fully extended V6 address. That was the good news. That was the easy news. And that was the best news for the bad guys. Because all I have to do is now take that 64-bit number, uninvert the bit, take out the FFFE, and they got a real MAC address. They can go look at the OID on the IEEE website, find out, oh, that's a Cisco router, oh, that's a Cisco phone, oh, that's an HP laptop, oh, that's a HP printer. Thank you very much, right? And then all they have to start looking and trying to determine is, with that OID, can I tell what kind of devices are on this network segment? All right, so they can determine how they want to start their attack. So that was a good idea, but not real practical. The other option is a interface ID can be generated using a random number generator process to generate a 64-bit number. Microsoft spearheaded this, it became a standard, so the operating systems, when they need to self-generate an interface ID, can use either one of these options, the random number generator or the modified UE64. Most client-server operating systems now, in 2016 plus, are using this. Not necessarily all. Windows has for years. Apple finally started in, I don't know, somewhere around maybe 10.8, maybe more like 10.9. Linux, who knows? Luck of the draw on those. Most router vendors, if they're generating, they use the MAC address. And most of them don't even have the option for the random number generator. The client-server operating systems, you can pick and choose. You can say, whatever the default is, I want the other. For most of them, they're happy to do that. Now, the other thing about the random number generator is it generates two 64-bit numbers that are used for the interface ID. One, basically, that you get, and the second one called the temporary. The temporary was an added feature to say, hey, not only do we want something that looks random, but we need it to change so that Jeff isn't using the same random number everywhere Jeff goes. Then they were no better off than the MAC address. Okay? The downside to this temporary number is it can change. Why is that a downside? You're troubleshooting a client-server application, ding, 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 packets flying, all of a sudden packets stop. Woohoo! It's them. No, it's still going. It transitioned to a new interface ID in the middle of the process. Legitimately transition. Legally transition. Transition without dropping data. And the next thing you know, you're sitting there going, what happened? And you go look at the client, and you find out it's got a new temporary address. Yes?
That's why I like to make the customers do Wireshark captures on the client and server side.
Yes. So you see both sides, even if the address changes. Now, the transition of that, i.e. how temporary is temporary, is left up to operating system programmers. The standard doesn't say how often or when or anything. Microsoft, Windows, I actually can't say I've tested 10, but at least up through 8.1, and I believe 10 probably the same. If you bring up your client, Windows 10 or just Windows computer, it uses this default, it will generate a temporary, as long as that interface, that Ethernet interface is energized, i.e. it's still powered up, all right? then it will keep that address for 24 hours. It writes it to soft registry. At the end of 24 hours, it'll basically do the DAD for it again. Nobody else should have it. I'll keep it for another 24 hours. It will do that up for 7 days. At the end of that 7th day, it will generate a new temporary address. If you power down, unplug, short the port off, any of those things, de-energize that interface, it will start fresh. Apple, at least again up to about 10, 8, or 9, every hour gets a new address, a new temporary. And they haven't even really spent any time looking at Linuxes.
You said if you shut the port, it'll do it?
So again,
If you shut the port?
yeah, if you shut the port, it will get a new one.
Wow, that'll be helpful.
But
The network guy.
isn't that also working with DNS or zero touch provisioning?
Some operating systems are happy with that.
I understand.
Your mileage may vary. Soup of the day, test your world to see. There's not a good answer on a lot of this stuff
That's,
because of that.
that is part of security now. That is part of the security model of security
Yeah.
in a /24. Makes sense.
Most client OSs that work with the random number also allow you to turn off the temporary address function. Microsoft Server 2008 and above does not use the temporary generation, but it uses the random number. It has the temporary shut off so that it won't change. Okay? So the temporary address, if available, is the most preferred V6 address. Which means, remember I said a while ago you could have the 4 global unicast addresses, one from DHCPv6, one from static, and upwards of 2 from random. And of the randoms, the temporary is the most preferred out of all 4. Static, who cares? DHCPv6, who cares? I got a temporary. That's going to be my source GUA address. That is not my expectation the first time I saw that. I thought my static address would be the best preferred, most preferred. It is not. The temporary, by the standard, is supposed to be the most preferred because it's considered the most secure. Because it changes. Means you can't be found. Which is tearing us up troubleshooting. All right? Because again, if you're only looking at one place, or actually only looking at one address, or a pair of addresses, or that client address to anything, and then all of a sudden packets stop coming through with that address, but things are still working, that means a temporary just transitioned. And it's just unbelievable to see the first time, because you're like, no. Because in a V4 world, something like that, things break, or hiccup. Or as we would say here in Texas, get a little hitch and a get along, right? A little temporary pause and then it might pick back up again. But in a V6 world, you don't even see a blip. And part of that is related to timers, address timers. In the V4 world, we only have one kind of timer on a V4 address, a lifetime timer. If you statically assign, it's infinite. If it's DHCP assigned, it's assigned a lifetime by the DHCP scope, or within the scope. That lifetime could be minutes, hours, days, weeks, months, years, okay? But it's a lifetime. In V6, we have 2 lifetime, operational lifetimes now, one called the preferred and also the valid. And the way this basically works is when I first come up and I get an address, whatever process I get an address from, I first need to validate it's valid for me to have it. I got to do the DAD test, duplicate address detection. Once I basically discovered that it's safe and okay for me to keep this address, my preferred lifetime and valid lifetimers effectively are working. The preferred lifetime is less, typically 70% less, or 30% less, or 70% of the valid. What this means is that during the preferred lifetime, I can start new communications, I can keep going communications. At the end of that preferred timer, I can no longer initiate new transactions, but I can continue finishing up old business till the end of the lifetime. During this bit of time where preferred is no longer usable, the OS should basically either go ask for a new one or rerun the DAD to validate it's okay to continue. And then all the timers start over again. This process also allows us to readdress a network segment in the middle of the day, in the middle of production. Because I've got, let's say, network 2001 DBA:1:2, and I want to transition to 2001 DBA:2:3. So I fire up my routers to do what they need to do. The clients get this new address. They've got their old address. They finish up their business. They start the new business on the new address, and nothing drops. So you could re-IPv6 a network in the middle of the day without a hitch. That's also how that temporary timer, that temporary address can transition to a new one, because it's got time. When old businesses finish up and it goes to get another temporary address, if it gets a new one, all the new communications start with the old one while we're still finishing up the transactions here. And that's why things don't drop in a temporary address transition. That's why you can readdress. If I say things like re-IP address a network in the middle of the day, who just got those little cold shudders down the back? Say, yeah, you on what production network you did that on, right? No, we would never think that, because they're not successful with the best of planning. There's always some little something squirreled away devices or people that didn't read the email, right, on that V4 network that still have to go be touched. We still, for days after this process, we're getting calls. But we could do a V6 world in the middle of the day. I'm not advocating that we should. I would, of course, take a maintenance window, but I guarantee you it will be the easiest one you ever did. Okay? Because you'll play the Scotty syndrome. Yeah, boss, we need to take a 4-hour outage. We're going to re-IP the whole corporate network. 20,000 addresses we're going to do. 4 hours, maybe not even enough. Well, let's just say 4 hours, and you accomplish it in 15 minutes. And that's just because you had to go spend time looking everywhere to make sure it worked, not because it didn't work. But you keep the 4 hours. Say, yeah, boss, boy, it was tough. We got through it without much problem. Yes.
So, how does this affect applications that may be keeping track of sessions via IP addresses, dynamic ACLs and firewalls, load balancers?
Well, that's kind of an interesting thing, because you still have to build the network side of all those devices. The applications themselves should be relying on the stack to take care of business. And as long as the stack is taking care of the addresses, then the applications shouldn't be affected. But there's a key there, right? There's that should. Mm-hmm. So that becomes one of those, how deep in addressing are the applications? And so you just, that then takes the point you got to test. That's where you then find out that temporary addresses, bad stuff. Turn that thing off, right? Readdressing in the middle of the day, no, we wouldn't do that ever. All right, but you have to test. In theory, if they're not that deep and they truly are relying on the stack, it should be not seen. But I know there's a whole lot of stuff there to say in theory.
Yeah, I agree with you saying, because you got a stable connection to a firewall. Now, if interest changes, there's no send and send act. How does the firewall?
Well, but part of that too, remember, is if at this point, if my preferred lifetime has ended and I want to start a new session, I can't. The stack basically says, got no address to use. You've exceeded your preferred lifetime. I can't start anything. But I can still finish up those existing sessions because I still have valid time.
So the existing session won't change IP address. It'll keep that same address to that session, then.
Yes.
Then okay.
Yeah, exactly. So that's why if I transition to a new GUA, because the old GUA preferred time ended. He's still got his address, he still can finish work, but my new one kicks in for all like new sessions.
But that doesn't.
So this, that's become part of, again, you really gotta make sure of all the end-to-end does do the work and supports it.
There's a lot of applications though that do licensing based on IP addresses and stuff like that.
Well,
No
now,
one's doing licensing.
okay, let's say this. Everything I'm talking about really from this dynamically changing is dynamic address assignment. Static addresses in V6 still have infinite lifetime. So a static address, really, this goes away. It doesn't really matter because they're infinite. So from a licensing viewpoint, from your core components, we're still going to statically assign, or maybe reservation DHCPv6 assign, all right? But still, same kind of thing applies. You're going to have long time or infinite time.
Okay.
The only time you'd ever really see, I would say, these kinds of things working is client side. I've never on,
Well, yeah,
at least not for me, never on infrastructure.
But that's what, I'm even talking about that. This is version 4, but specifically like the ASAs you had 10 licenses or 15 licenses. Well, if you change that IP address, you now have a new NAT session going through there. The other one doesn't expire for 5 hours or 10 hours.
You said NAT.
I said it was IPv4.
I know.
Yeah, but that's an example where you have a client device. You only have 10 licenses for your ASA, and you've gone and changed IP addresses, and now you can't get out to the internet anymore, and you figure out, well, I've got 10 unused NAT sessions sitting out there that are sucking up my licenses, or I've dealt with an application that was had some mobile trucks, and you log back in, or you logged into the system, got your tickets and stuff. Those sessions, those IP addresses were tied to the user account that logged in. So, and there would be issues if they were to, because they were mobile trucks, if they were to transition to a cell that changed their IP address, they would still work, but they would get somebody else's ticket now because that IP address was associated with a different user account. So that's just stuff that's going through my.
These are the things, absolutely, you have to go through. That's part.
So what I'm seeing is one thing that I see a lot of times on a network is our own network, is you'll have the computer won't want to work properly, and you do a little digging on it, and it says, oh, restart your computer, you're on somebody else's DHCP address. And I'm like, what? Okay, never mind. So you restart the computer, you get a new DHCP address, and then you're fine. But from what I'm understanding, from what you're explaining here, that's not going to happen anymore because this is automatically taken care of with IP version 6. Is that correct? The right way to think of that? Because it would be theoretically impossible to grab the identical DHCP address that somebody else has.
In all things working good, yes, I would agree.
Okay.
All right, because I still potentially have issues of devices statically assigning an address that sits on somebody else's. I can also have rogue devices that are answering to every gas, just like they answer to every car. Yeah, I got your 10.10.10.2. Yeah, I got your 10.10.10.3. Yeah, I got your blah, blah, blah network, colon 1, colon 2.
Right.
So that's why I wanted to clarify. The problem isn't necessarily any less of an issue, V4, V6 from that perspective of a duplicate. So it's kind of, it's really kind of, I don't want to put my foot down and say, oh yeah, it's all fixed. No. It's not. It's not any worse. I'm really going to say it. I don't think it's any better. It's pretty much got to be considered equal.
So it's still gonna depend on having a good IT sysadmin to configure things so that you don't have these problems.
Exactly. Yeah, so nothing changes really from that perspective. It's just different numbering.
Okay, good.
Bigger numbers, different numbers, the whole bit. Yes, I would go with that.
So when I'm asking questions to qualify an IT sysadmin for a particular position, and when the customer has specified that want him conversant in IP version 6 addressing, then having him explain how to avoid situations like that is the kind of question that I should be asking.
At minimum, yes.
Yeah, I mean, along that range.
Yeah. And ask them to get into some details like this.
Sure.
Timing, the timers in V6 addressing, is what I have seen in my travels, the least understood, not even really known about. For somebody who says, yeah, I can do V6. 6.5, almost 7 years ago, I could do V6. I could turn it on, I could route packets, I could make things happen, I could do OSPF v3. I was very fine and happy. And I had no clue what V6 was about until I started digging, so I started looking at packets. Literally, so I started writing about it and having to read the RFCs and really understand, oh my goodness, just lighting it up and making packets go back and forth is not really it until there's problems. Yeah, it may work and life may be fine, but yeah, if you're looking for people with specific skills, you've got to ask some really very pointed kind of questions.
Oh, yeah, absolutely, yeah,
And get them to, draw the pictures or, really talk to it, not what the address is, not how to route it, what's the router ID in OSPF v3? Is it a 32-bit dotted decimal number, or is it a 64 or 128-bit colon number? No, it's a 32-bit dotted decimal number, but it looks like a v4 address in a v6 world, but it's not a v6, or it's not a v4 address, right? But it has to be set differently for OSPF version 2, and it could be the same router ID for OSPF version 3 because of 2 different routing protocols. So yeah, you have to get to almost those kind of details for people to reply back to. And that's where I found, like I say, for myself, I was all tripped up. I followed basic, I can make it work, but I didn't understand it.
Sure.
And really, understanding these things about how the applications are worked, understanding about what the temporary address does, really only makes sense when you see it happen. And even testing for some of it to see how it happens is not always easy. And when you're trying to build a lab environment up just to do things, it's sometimes a lot of work to set everything up just right. And then you miss it. And you know you missed it. And you go, ah. And sometimes it takes time. And it either is you got to let the operating system do the thing, or you got to completely shut them down and bring them back up again so that you can get the triggers to fire. So even in troubleshooting, sometimes it's a little more interesting in trying to find why things didn't quite work. I want to try to show a few of those things where timing is everything in this environment. A lot different than we had in V4. The quick little overview here in V4 world, your things like ARP and reverse ARP and some of your ICMP type of technology, they were spread around multiple RFCs. In V6, they're all kind of consolidated into the neighbor discovery protocol, most of your ICMP stuff. Things like we've been talking about, these router solicitations, router advertisements, neighbor solicitation, neighbor advertisements. These are all in one space. It's handy, but sometimes a little challenging. For especially what we're looking at tonight and in general purpose, these are the predominant, I would say, infrastructure ICMP packets that you'll be looking at. In your early bits, and maybe even just initial troubleshooting, my first go is I'm looking for router advertisements. Because in a V6 world, the router is in control of a lot more than just basic routing. The router advertisement has those bits in there that tell the client how it should do its addressing. Whether you use the network prefix I'm going to give you, says the router, and you figure out your own host ID. Or, now, why don't you go ask for a DHCP v6 server to give you an address? Or, tell you what, I'll give you your network prefix, you figure out your interface ID, but go ask the DHCP server for DNS, domain name, time server, download server. So it's a half and half. And then, my most favorite, all flags on. Here's a prefix and ask for DHCP6 server, and the client will do both. And that's all of a sudden how it gets 3 addresses, or upwards of 3. The DHCP one, and if they're using the random number generator process, that one, and the temporary. And which of those 3 will it use? Temporary. And that will not be your expectation. Your expectation will be, use that DHCP address, because I trust that one. And the operating system, yeah, fine, thank you. But it's usable. You can use it. You can source from it purposely, but by default it won't be. So router advertisements in a V6 world are like crucial. We are king. We own it, and we can mess things up just like that. All right, and we're going to see that. Router solicitations, those are the clients, again, just say, hey, is there any routers out there? So these are some of the key packets we're going to look at. The duplicate address detection. Quickly on that. The problem in the early days, we'll back up to my timer slide, was you had this time interval called tentative. During tentative, you are not supposed to use that address for real stuff yet. You should move from tentative to preferred. All right? However, tentative state might actually equate to 2 to 3 seconds. And 2 to 3 seconds in a network these days is way too much time to wait. I'm pressing the go button, I want things to go. Well, the problem with that tentative state is this was what's happening in tentative state, the duplicate address detection. And basically, I'll say it in ARPing for myself, it's the same concept, right? I'm sending out a multicast on-link message to myself to see if I reply. If I don't reply, I can keep that address. That's the tentative state. So they augmented the standard to say, tentative state lasts for like that long. Do your DAD, but you can also use that address right off the gate. Now, if DAD fails, you got to back off and try again. But that means now you might have started something. It might mean you actually stepped on somebody else. All right? So the DAD must run for any IPv6 address. Link local, DHCP assigned, statically assigned, router advertisement assigned, however it's derived, it must do a DAD. It must validate for me that address is unique, and I can keep it. So the tentative state will be very minimal in general terms. It's actually hard to even see, like in Windows or in Mac OS, you can execute commands, of course, to see your addresses. You can see the state. And that tentative state is a blink, typically, these days. But the duplicate address detection must run for any address, for any device. Any IPv6 enabled interface is supposed to do the DAD. So you'll see those kinds of packets out there. Now, the chart. And this is going to come into real specifics, issues, or not issues, going to point out some specific issues in a few of our lab slides. The router advertisement packet has 4 specific bits that are dealing with telling the client how you do your addressing. If I have anything to say, I being the router, I have these bits that I set in a specific combination. The default combination is called SLAC, Stateless Address Auto Configuration. The 2 specific bits are known as the A flag and the L flag. The A flag is basically auto assign, kind of the shortcut. The L flag is basically says, I'm your on-link router. That is the default setting, at least of every V6 router operating system I've come to, whether they're classic routers or firewall routing or any V6 routing enabled type software. They start off in SLAC. The downside to SLAC is, the SLAC says a couple of things to the client. I'm going to give you your network prefix. Here's your 64-bit prefix. You figure out your interface ID. They've got 2 choices. I don't care. I'm the router. However, with all that said, the client has no DNS, has no domain name, download servers time, so they have nothing else, so it's practically unusable in our world today. So there's an option to that called stateless DHCPv6, which is the A and the L flags on, and another flag called the O, stands for the other configuration. This tells a client, here's your prefix, I'm your router, go ask a DHCPv6 server for other stuff. Other is DNS, domain name, download time, blah, blah, blah. All those other things. No address, just everything else that a DHCPv6 server can give you. And then it becomes usable. If you instead say, well, really today we do DHCPv6, you need to have the M flag on, which stands for basically managed addressing. That flag, if the client sees that in a router advertisement, tells the client, go ask a DHCPv6 server for an address and anything else it can give you. Most vendors in their documentation will tell you, you want DHCPv6, go turn the M flag on. You turn on the M flag. What other flags were already on? The A flag and the L flag. L flag, leave it on. A flag, you actually want to turn it off. You don't want to give that client a network prefix and tell it to generate its interface IDs because you wanted the DHCPv6 server to work. Most router vendors don't tell you all that story. They just say, you want DHCPv6, turn the M flag. And the next thing you know, you've got 3 global Unicast addresses on your client using the temporary. And you go, no. I've got a managed address world. Why are we not using my managed address? Because you didn't turn off the A flag. Because the router docs didn't explicitly tell you to turn off the A flag if you want to use the M flag. Ask me how I know. This is why this chart came up. I'm running this stuff in the lab and I'm getting all these, okay, stop. You have to scratch it, rebuild from ground up, and go through it in methodology, right? Okay, what flags are on? What did I get? Okay, let's do what the docs say. Turn on the M flag. Now, whoa, this isn't good. And somewhere else you may read in their documentation, oh, by the way, at least half of them you didn't even get that. You had to figure this out on your own. That's why literally this chart came up for me, because I was so confused. So what you don't want is all those bits on. A, L, M, and O. Now, if the M is on, the O flag is irrelevant. Really. Because the M flag is everything. The L flag in the RFC, in my interpretation, it says basically, you know what, the L flag doesn't really matter. And I found that to be true with Windows. I can turn the L flag on, I can turn the L flag off. That's still the router. Windows was happy. In Mac OS, if I turned off the L flag, but left the A flag on, it would do its addressing, but it would not see that it was its router because the L flag was off, even though Windows liked it. Okay, now that messed me up. So that's when I went back to the RFC and said, well, really, the L flag doesn't matter. Well, some vendors it does. So again, kind of why I did the chart, right? L flag, if you want this to be your router, just leave it on. Although some operating systems, even if it's off, may still think it's its router. You have to be a little careful. You have to test. You have to test everything. This is where Wireshark becomes your friend. This is why you're going to set up some special display filters in Wireshark to make your eyeballs' life a lot happier. Your eyeballs and your brain happier. When you're looking at this kind of, I was going to say nonsense, but nonsense when things aren't working. Why aren't they working? Actually, it might have been working too well. All right? You got a lot of IPv6 addresses. Woohoo! That's not a good thing. Link local and maybe 2 others is where you want to be. Now here's the fun part. In some client operating systems, if you statically assign an address, but you get a router advertisement with the M flag on, guess what they do? They do what they were told. They go ask a DHCPv6 server for an address. So now you've got the static and a DHCP. That is not a desired result. So then you have to make sure you turn off the M flag if you want that static to be there. And in most operating systems, you can. But there's not an override. It does not always work like v4. In v4, in most operating systems, if you statically assign, they never DHCP for an address, do they? They'll start out that way by default. They'll send out a DHCP request. And if they don't get a reply, then they'll default to the APIPA. If they've got a static, they just start using that. The APIPA's gone, they don't DHCP. No such luck in the v6 world. The clients are supposed to do what the router advertisement tells them, regardless of everything else they have statically configured. In Windows, there is a box to put an IPv6 default gateway. When you go in and statically assign its address, there's a box. Do not fill in the box. Will it work? Maybe. But what address will you probably put in that box? The link local address of the router or the GUA address of the router? Who votes link local? Who votes the GUA? Who's like, I just don't really have an idea yet. Just shut up and tell us. The link local if you must. Because all communications on a link will use link local addresses. When you talk to your router, you will use your link local address. It will work with most operating systems if you put the GUA, but you're just not supposed to even do it because the router advertisement tells the client, I'm your router. And that's the way it's written. That's the standard. So humbly, Microsoft should have taken that box out. But I'm guessing they just copied the v4 code to make it work in v6 and left it all there. Like I say, it will basically work, but it can actually cause other problems, potentially. So if you're statically assigning v6 addresses, don't put in the default gateway. Let the router do its job. And that's going to mess up now also the DHCP server folks. Because I'm the network guy, all right? I'm going to tell the server team, here's the networks for all these different VLANs. Here's your network prefix, here's the range I'd like you to use, blah, blah. And they're going to go, where's the default gateway? Stupid network guy. First thing they're going to do, they're going to come chomping, network guy. You still have a clue, do you? What's the default gateway for those networks? And then we get to say, silently, stupid server guy. You don't have to know that. I'm taking this the Obi-Wan way. You don't have to know that.
You don't get to do that.
My router is taking care of business. You don't get that. The best part about it is there's no field for it in DHCP-v6 server applications because they don't need it. Now, there is an RFC that's been in draft status for about 3 years for people heavily complaining and lobbying against that because that's messing up 15 years worth of what we've been doing. And humbly, I'm just like, really, get over it. Just do what the specs say. But I'm very zeros and ones thinking. So again, understanding what you see with what should be and what you actually have are different in v6 kind of compared to some v4 because we have nothing like this in v4. It was very easy in the v4 world, the v6 world. So we'll see some of these potential issues in these packets. I got to shut up. We got to get going. The DHCP v6 process is similar, just a different acronym. Instead of DORA, it's SAR. All right, solicit, advertise, request, reply. I send out a multicast message, an on-link multicast, looking for a DHCP v6 server to reply. Whether it's on link or my router is doing DHCP v6 relay, I don't care. All right, it works just like it does in v4. I get back an advertise message and say, yeah, I'm your server. What would you like today? I'd like an address. Please, here's your address and everything else I can tell you that you asked for. DNS, domain name, time server, download server, blah, blah, blah. Okay, so it's effectively the same, just a little bit different looking. But, well, no buts, period. All right, just a little bit different. Wireshark. So let's look at Wireshark. Color filters. I lobby heavily for coloring certain kinds of packets, like router advertisements are orange, router solicitations are pink for me. in Wireshark, ICMP and ICMP-v6 packets are both the same color.
Say that again?
Really?
Say that
Okay, well, I'm turning off V4 anyway, so I don't care.
Say that again, I missed it.
ICMP
Yeah.
and ICMP-v6 packets in Wireshark are the same color. So I changed my V6 ICMP to be a different color, yellow. I want to see this type of traffic flying by a live capture, or if I'm looking at a static trace. I don't necessarily always have to go look specifically at them, although I will be. I just need to know they do occur. Router advertisements have two kinds of basic timing. When a router interface first comes up, there'll be 3 router advertisements right out of the gate. Bang, bang, bang. And then periodically, approximately every 6 to 10 minutes, a router will just say, here I am, without request. Now, clients, if they came on right after a router advertisement, they're not going to wait 6 to 10 minutes. So clients, when they first come up, will initiate a router solicitation, and I should see a router advertisement very quickly thereafter. So, hence, pink and orange. There's pink and there's orange right behind it. I'm thinking so far, life is pretty good. You know, if I'm either troubleshooting or I'm doing my initial tests, I want to see these things happen. All right? Most router code, or any route-capable code for V6 routing, you can change that router advertisement timer. For lab use, put it down to like, 60 to 180 seconds. Because 6 to 10 minutes means you're going to be sitting there waiting a long time. Now, if you're on the clock, woohoo! Don't change that puppy, maybe bump it up a little bit. I'm just kidding. But most of the time, we want to see these things occur. So for initial lab testing, I usually put my route advertisement timers down very, very low, a couple of minutes apart, because I want them to occur, and I want my clients to react, because I got to see stuff happening, right? And then maybe I'll kind of bump them up later from that point. But that's why I really, in V6 even more than V4, I really use colors. And you don't have to use my coloring scheme. You do whatever. And you don't even have to. If you don't like colors, that's fine. Maybe change it to gray, different gray, if you don't like the color. But, you know, it's just handy to be able to see the stuff flying past. Oh, there went an orange. Okay, router advertisement. Oh, there went a pink and an orange. Okay, there's a new client came on. All right. Okay, it's been a while, Oh, another orange. Okay, router's still there. Just to do that initial learning, to get that initial bit going, and it's going to help here in a little bit. Color rules, you set them up, play with color rules. Display filters, there are 3 primary V6 filter definitions in Wireshark. IPv6, ICMP-v6, and DHCP-v6. Now, under all of them, and especially the top 2, there's lots of other things, right? Deeper levels, but there's the high level. Display filters in Wireshark, if you're not a big user of them, will help you in your V6 troubles. Because one of the things you can do, just turn on an IPv6 filter and all your V4 stuff is gone. Not out of the trace, just out of your view. Okay, because you're probably not caring about the V4 at the moment. I just kind of need to see about some of this V6 stuff. So get rid of it. Take it out of the view. And then, as you're going to see in all the little mini labs here, very specific focus on specific type of traffic. Get those display filters going. And then remember that, and I'll back up to that here in a second. Where is my columns? Configuration profiles. I talked about this last time. I talk about it all the time. We talked about it tonight. You can have different configuration profiles which have different display filters, different coloring rules, and a few other options as well. So again, I can tune my eyeballs quickly. I need to look at some V6 traffic. I got my favorites, all my V6 favorites under a configuration profile. Oh, I need to look at some router advertisement details. I've got another one just for that. I've got different columns that I'll set up, and that's what part of this was back over here. Whoops, wrong way. I'll set up different columns. In display filter building and in column building, you can go into the packet deep, wherever you want. Right-click on an area and either set up a filter or set up a column. I'm going to do some of that tonight. We're going to do some of that tonight. You don't have to know all this stuff. You don't have to look it up. You got the packets. You got everything you need right there. You can build this stuff very quickly. It's all portable. The configuration information is portable. You can share it with the rest of the team, put it on a shared drive, send it in an email. It's a few little files. You can put it under each configuration profile in a folder, and then it's got all of its display filters and color rules right there. So it's portable to the team. Or like me, it's portable to all my computers in the lab. Once I get something built up, I put it on a shared drive, I go get it, put it in the folder, and now I've got it. And all my Wiresharks are basically the same no matter which computer I get on. And I get on like a dozen different computers in the lab all the time. So all those little tips and tricks are what we'll talk about tonight. So it's time to play. If you've got your computer and you've got this file, and if you didn't get the file locally, you'll get it on a flash drive. It's also up on that box.com site. So one of the things I want to do is open up this file and let's create a configuration profile. And then let's get a couple little things set up in Wireshark so that we can actually quickly maneuver through this trace in trying to do a little bit of troubleshooting. So with that said, let me bring up my Wireshark. And I've got this file open. So one of the things I'm going to do is go down to Edit, and we'll build a new configuration profile. Edit, Configuration Profile, and I've got a bunch already. I've got one from the meeting last month. So I'm going to build one for today. So literally, I'm just going to do a copy of this profile, or I could create a new. I'll do a copy of it. And I'll rename it from December to January. And I click on it. And even though you won't be able to see it on the screen, in the very lower right corner of your Wireshark, you'll see Profile and whatever you named your new one. And if you click in that box, you can find all of your other profiles that you might have. And I've got a bunch. You can see I've got some for V6, I got some for OpenFlow, I've got some for some workshops, I got some from some other projects, blah, blah, all kinds of different ones in here. So I'm going to use this DFWCUG 2017. So your default view would probably also have the packet bytes screen. You know, all that hex stuff down there. I don't know about you, I'm very rarely myself in that space. It takes up real estate on my screen. If you go to View and just select the Packet Bytes option, deselect it actually, the packet bytes are gone. And then I don't have to worry about that. If I need it later on, I will typically maybe only need it when I finally found the magic packet to go blame the server team. Okay, then I might need it. I can bring it up. But for the most part, it's visual noise to me, or audio, yeah, visual noise, audio noise, visual noise. It's just noise. It's extra real estate. Right now, I've got this trace, and if I just go through, even not too slow, you can see some of the different colors flying by. You can also see I got some V4 and V6 addressing in here. Now, another really way cool thing that's come out in Wireshark 2.0 and now even the newer versions, you should get the latest one fairly recent, 2.2.3, all right? In 2.0, I guess in 2.0, they added a color bar on the right. It was actually an integrated scroll bar. And a lot of us complained about it, and they moved the color bar over and they brought the right-hand scroll bar back. This color bar also helps you go, oh, look, all those little orange bars, what are those to me? Router advertisements. And if I had predominant others of colors, I would be able to see that a little bit easier as well. One thing I can very quickly do is just come up here and say, in my display filter, just type in IPv6, hit the enter, and it filtered out of 89,000 packets. Now I'm only seeing 43,000 packets. Now I'm only seeing my V6. So my color bar, I get a little bit, you know, 50% better granular detail on it. As I move my scroll bar to different areas, I can see the color. I can also just go click on an area of the color bar and jump to those packets. There's some really handy, just minor little things that can make a lot of difference in Wireshark usage. Let's just basic all the V6 packets, all right? Just wanted to play with some V6 work. So we turned off packet bytes. We created a profile. One of the things I typically do is change my time down to sometimes seconds, sometimes milliseconds. It just kind of depends on the granular detail I'm trying to go to. And the only other thing I was doing is I add a delta time column. So if you want to add a column like that, you go to Preferences, and you say, oh, no, that was the wrong spot. Wait.
Columns, appearance columns? Add.
Yeah, columns. So I'm going to click down here, new column, and I'm going to call it delta. And then what I'm going to do is go find the delta time displayed, and I'm going to move this up to between time and source. Why do I add the delta time? Router advertisements is where I use delta time. I want to see between router advertisements how long the time was. Was it within 6 to 10 minutes? Or was it within like 1 to 3 minutes? Or is it something different? I just want to know this data, and the delta time becomes handy. So with that in mind, I might say, well, let's look at IPv6 router advertisements. I just want to see out of this trace of 89,507 packets, how many router advertisements I had. So that's an ICMP v6 dot type equal 134. If you'll notice in your display bar or display filter bar, as you type information, it changes colors. Red means whatever you're thinking you're looking for is not real. Yellow means there might be some similar. Green means you dial it right in where you want to be. That's a valid field in the packet. And so now I filtered out of 89,000 packets, 1,266 are router advertisements. All I'm looking at now is router advertisements. Just a really quick thing. And right off the bat, something just jumped right out at me. Does anybody else see anything that just might jump out all of a sudden? With wherever you are looking router advertisements, do you see anything there that might look odd? If I give you a hint, I only expect one IPv6 router on my network. Now, does that help you? I have two. Look at my source addresses. I have an FE80 : big long number ending in 5 Fox 8 Charlie, and I have another one ending Fox 252. Link local addresses that are sending out router advertisements. I only expect to see one router on this network. What this means is I got another V6 router that I did not put in. And another little interesting tidbit. This link local address, FE80 : F252. Do you think that might be the rogue? Or do you think this other guy might be the rogue? And in this other address up here, was that generated from the modified UE64 format, or was that generated by the random number generator? UE64. Look right in the middle. FFFE is your key. Does it not mean it could be random? It could be random, but the chances are pretty slim, right? But it doesn't mean it could. So of these two addresses, the 252 or the modified UE64, which one do you think is possibly not the real one? The F252? Anybody else want to hazard a guess? I haven't given you anything else. I'm just saying, look at addresses. What would you think?
UE64 is false.
Say again?
UE64 is fake.
Got the U64 ones real, or you're saying the same thing?
No, I changed my mind because
From class, they said it's easier for you to configure your link locals, so it's easier to identify than trying to use a randomly generated one and keep up with them on your network. So I'm gonna backtrack and I'm gonna go with the randomly generated one.
So you think this is the real router?
Possibly, yeah.
And that's, in your kind of definition, you think that guy might be the road.
That might be the road.
Okay, and you're saying the opposite. This is fair. This is good stuff, because you brought up the great point that I wanted to point out. This is the real router. Because on router or route-capable operating systems, although I will say not all firewalls that can be V6 routers can do this, and not all real routing protocol vendors yet, but most of the router vendors allow you to statically assign the link local address. And here is the primary reason. What happens if you've got to take a router config and put it on a new replacement router, and the static configuration had this address that had been, quote unquote, not so randomly generated, but had been pulled from the internal MAC, but now written into code, into config. And you now put that config on a new router, and it's not the MAC address, and it's going to try to do something different. This is why on router interfaces, it is a good idea to statically set that link local address, and that will override using the modified U64 format. And now that config is 100% portable to any other router. And you'll probably want to do something that's a little bit easier to understand.
It's also more often.
Don't do FE80::1 or FE80::254. Those are the first two addresses the bad guys are going to check. Actually, they're going to probably check ::1 through 10 and probably ::250 to 254. Who uses .17 for their router address? Now, depending on your subnet mask, blah, blah, I get it, okay? But just generically, we either use one end of the spectrum or the other of an address block. So don't do that easy, even in your static link locals. I have not found the capability of setting link local addresses in client and server operating systems. Okay? It's the choice of the other two. But the router ones, most enterprise class routing operating systems allow for that.
I've had to set my link local on my Linux box because I had to set the link local on my Linux box.
Yes, you had to set it, yes. And I actually have seen that. It was like a little commodity router. You actually had to set the link local. It wouldn't pull the MAC address.
I mean, I had to set it to resolve a VLAN problem because it would see itself somehow untagged, and the dad would say, nope. And so I forced it to have a different link local on every VLAN. And it works.
Now and that kind of takes me into one other little quick question to point out. On a multi-interface router, whether it's a layer 3 switch doing routing and VLANs are the interfaces, or it's a classic port-by-port router interface, can the link locals on all of those interfaces be the same?
Yes.
Yes, and most likely will. Because the switch or the router only has sometimes one MAC. Now, the interfaces that are individual, like in classic router, would be different. But they can be the same. So your FE80::252, if you've got 30 routing interfaces on that box, they can all be the same link local. And you would want that because that's that router. You want to know for all those networks what that router is. So setting link locals in the router to your schema is way better than letting it come up with using the MAC address, because the config is less portable, and it's also a little bit harder to designate which router is that. But I know who that guy is. I built it, right?
50 with F252 written on the front of the router.
Yeah, we won't go there. It's and very honestly, mine was like 10.1.1.252. So I just stuck an F in front of it to be a little different. That's all I did in my lab stuff. So yeah, it wasn't that you would be able to pick up. This is kind of an illustration saying I've got two routers, but I know I only really should expect one, and I know which one it is, so I kind of know who the other guy is. What they're doing, we don't know that yet. and I'm not gonna go there yet. This is an illustration of, here's traffic, here's Wireshark, I've got a profile set, I've got a display filter set. Now, the other thing I would do is save these display filters that you're gonna use frequently, like the router advertisement, okay? When you save them, you get them over here on the right side. And so I've got V6, router advertisement, router solicitation, router advertisement, and router solicitations, okay? If I'm just looking at a trace and I want to see that I've got some traffic, and it's really hard to tell, but I can see it here. Look, there's a pink, a couple more pinks. Pinks are router solicitations. So if I go over here and look at this grouping where I've got some pinks, this client sent out the all points link local, any routers? And both of these guys said, yeah, I'm a router. And guess what? If these have different settings, those flags in their router advertisements, what's that client going to be doing? Hopefully, what it was told. Which now makes matters more interesting because we have started again looking at some of this timing. Now we got to go back and look at this client. Well, what addressing did he get? He would probably have whatever the last router advertisement he saw.
Or both.
And I could just bang, bang, and change my addresses that fast. I'm sorry, say again?
Is it the last one or the first?
Last one. Whatever I'm told last, it's the last thing I heard.
Oh, okay.
But what happens if my production router is going every 6 to 10 minutes? And that rogue router comes in there every 30 seconds? Those clients are going to be bouncing back, well, actually they're going to be stuck on whatever the rogue one told it to do, which a smart rogue would have first listened for router advertisements, see what the config is, and then make a different config, right, to bring everybody over to the rogue. Bring all the, we won't go there yet. But you kind of get the thinking of some of this, but I don't want to go too far with that. Okay, so that was some like real quick things we're going to do. Let me back up. I want to run some other tests. So I got a couple little things here. Let me bounce over here to the slide. We built that. I want to just look at some quick, like DNS type stuff. Because remember in V6, we are looking for a quad A record to do a DNS resolve, not an A record. An A record is that other old, antiquated 4.3 billion top address before. I don't know that. I can't speak that. I don't care about that. I'm looking for quad A replies. Okay? So the DNS had to be fixed. That means we got our DNS is all chimed up and our servers are all lit up with V6. Everything's all lit up. So I just want to look at a little bit of this stuff here with V6 and DNS queries so that I can view a few different things. So I've got that filter, I think, already built up in here. DNS query and execute. Now something right off the bat should just jump right out and make you go, I see a V4 address making a query for a quad A record. What in the world is that V4 address going to do with a V6 response? Nothing. But I'm going to log it now into my DNS resolve table, my local cache. All right? So I did a query using V4 to a V4 DNS. I got a response back, and it came back with a quad A record. And let me just open this up real quick. We did a query for a quad A, and we got a quad A. We got a V6 address on a V4 address request. We okay?
You're good.
Okay. We're going to what, 9:45, 10 o'clock?
Sure.
11.
Maybe not that late. All right. So another thing that occurred about 6 years ago, the operating system vendors, client operating system vendors, started making the V6 protocol enabled by default and preferred by default. So if you had a V6 address, you try to do things on V6. Yet you might have a V6 address, but you're not routing V6. So now you would try to do things like go to a website. It's trying to do a resolve to a V6 and never gets resolved. So after some number of seconds, that times out, we'll try on V4 as a fallback. And the experience was less than stellar. The resolve to it was known as an RFC called Happy Eyeballs. And Happy Eyeballs said, do everything in parallel. Do your stuff with V4 and V6 all at the same time. And for things like this, ask your questions in V4 and V6 for AREC and quad AREC resolve. So just like this V4 address made a quad A query, I can have a V6 address make an AREC query. Now, if that doesn't blow your mind, but remember, it doesn't care, the protocol doesn't care what it's doing and what it's getting. It's just taking that DNS resolve response and writing it to local cache. Then the stack will use whatever address it appropriately can. So the happy eyeballs in basically saying do everything in parallel means, and then whichever one you can use first, use it. So if you're V6 enabled but not V6 routing, you're probably going to be able to use your V4 first. And so it's going to get V4 responses, and it's going to start using V4, and basically things speeded back up. And that's what Happy Eyeballs, RFC 6555, gave us. It's not great. It's not 100% fixing everything, but it made life a little bit better. And most of the vendors have adhered to the Happy Eyeballs format. So it's even if you just say, let's look at DNS queries for a particular domain or a particular host, it's even understanding when you see things like this. Now the fun part is, what happens if you're running, say, Windows with 7 with Service Pack 1? Happy Eyeballs wasn't implemented. You had to get the add-on IPv6 Service Pack to get Happy Eyeballs. What if you're running Windows Vista? I don't think they ever updated it with Happy Eyeballs, but it was the first protocol with V6 built in. What happens if you're running built-in? XP had a beta test V6 protocol add-on that kind of sort of worked, but not really well, and Microsoft basically said, don't use it in production. Use it for test, but don't do it in production. Windows Server 2003 had an IPv6 add-on protocol. Don't use it for production because none of its applications use it. If you want DNS in Windows 2003 to work with Quad A records, you cannot. Not with Microsoft's. You got to go to 2008. So but seeing even just a real simple little thing like this, where both protocols are asking both kinds of queries, AREC and Quad ARECs. And then whatever answers it gets, and it gets back legitimate answers in both protocols, in both requests. It's writing all that to cache. Okay, I got an AREC for www.ipv6sandbox.com, and I got a Quad AREC. Woohoo! And it looks like V6 is kind of working here. So this was just kind of a real quick looking thing to see if anything looked a little odd. What else do I want to do? I think we'll leave that one. Oh, here's another interesting tidbit. In, I think it was 2.0 Wireshark, they added another really handy operation over in the far left side. You can click on a packet, and if there is a quote-unquote reply for that packet, they've got these little arrows that show you where they are. So I can see I made a query, and I got a reply, and the little arrows basically tell me these two packets are connected. Its query and reply is here. If I come down a little bit lower, I find out this guy looks like he made a request but never got a reply. This guy did. This guy here made a request and it looks like he might have got a couple replies. This guy here, he actually another quad or another AREC. And then we see that this packet over here is in a reply to something that I missed. Its question was asked before I got the trace, before I started my trace. So it's kind of an answer hanging. It's nothing wrong. It just means I missed the question, missed the query packet. in my trace. So it's another little, it's not always 100%, but it's a handy other little tidbit to try to track what packets go together. Okay. We're going to have, I think I'll move down to the RAs again. Okay, so let's do that. So looking at RAs one more time. All right, did this just a minute ago, but I want to go a little deeper. We're going to look for router advertisements, and then let's go look at one of them and look at how their flags are set. Finding these flags in the early stages is not really intuitive. Where are they? All right. Okay, one, the packet can't be that big. Agreed. But where in the level of the packet do those bits live? And then, just looking at those flags, you ought to very quickly and easy remember that chart and be able to tell, okay, which process is this router telling the client to get its address? Slack, stateless DHCP, stateful DHCP, or no flag set is how I'd want it if I'm doing an all manual, an all static configuration with my clients. I don't want the flag set. Well, maybe the L flag, the on-link flag. So, now that I've got these flag, or these display filters built, I'm going to go up to the top of this trace, and I'm going to select that first packet, 221. And what I need to do is bury all this stuff, because looking at the trace, looking at the packet, I'm going to go into the ICMPv6 bit, and I can see it's an ICMP type 134, router advertisement, nice and easy. I see flags, woohoo! But all the flags aren't there, only some of the flags. The first flags at this level are effectively, the ones that I care about at the moment are the M flag and the O flag. They're both set. So this tells me what? Use the router advertisements prefix that it gives to the client, or do a DHCP request client. What's the M flag? DHCPv6. So this is telling the client do a DHCPv6 request. Somebody else is going to give you your address, not me. But wait a minute. I got two more flags. Actually, one more flag I really am cared about, the A flag. The A flag is down here underneath the prefix information flag. And there it is. The A flag tells the client, here's your network prefix. Figure out your interface ID. And I also told you to go ask a DHCPv6 server. So how many GUA addresses am I likely to have on that client? 3. Could be 2 if I've turned off that temporary function, but it could be up to 3 in the same network prefix. 2 because of the A flag and 1 because of the M flag, the DHCPv6 server. And if via the Slack process, random number generator, I do also get that temporary, of those 3, which one is going to use? Temporary, which is so not what I would want if I'm doing DHCPv6, because I would want that to be my address. So we now start looking at this going, well, is this the production router, or is this the road router? We look at the prefix, we kind of already said this a while ago, but let's go look at the router advertisement for the other router, the 252. And we see here, the M flag is set, the O flag is not, and the A flag is not. So the M flag is set, the L always is set for Jeff. So this says do DHCPv6 only. So this further clarifies that this is probably my production router, and the other one is the bad guy router. Now, what's even more fun...
I got a question. If you look at the other flags on that one, it has M set, but not O.
Correct. With M set... Where's M? Oh, I can scroll up. Hang on.
That's at the other set. Flag.
With M Oakland. Because M says, ask for your address and anything else you need. The O is more typically used if the A flag is on, but I still got to get that other stuff. That's where you would see O. If O was on here, it doesn't hurt. The client effectively ignores it. So it kind of sort of doesn't matter if M is on what the state of O is. If you put it on, it won't hurt. Most router vendors documentation will say turn on the M and O. I personally disagree with it, but it doesn't hurt anything. Doesn't buy you anything, doesn't hurt you anyway. The client doesn't do a second request, it just ignores it. So that part is good. But yes, that's why in mine it was on. So this further clarifies to me that I see M and A both set, that in this router advertisement, that this is probably not my production configured router. And there's another telltale sign. Look at the router prefix that with the A flag the client's going to use. FD. Is that a routable to the outside world address? No, that's the ULO, unique local. Means I can run it anywhere in my router domain, but not across a provider. The provider should drop it if it even got it. We should not send it, but they will also be looking for that and dropping those in case we leaked it through. Just like you should on your inbound link from your provider, drop any from the FC00::7. You should drop them. They should never send them to you. But just in case something leaked, right? You got to protect yourself. So I find out that this client is going to get a DHCP address from probably the real network that this guy's using, and this guy's using 2001 DB8:lab:1001, and the bad guy router is using FD0. You only changed the first two nibbles, actually, yeah, the first two nibbles of the first hex tab. Everything else, it made it look the same. So it's very stealthy, right? If you're not really looking close, you just kind of look at that number as a number. Oh, yeah, DB8:lab:1001, yeah, we're good. All right? So that client's going to actually have a DHCP address in the real space and a ULO address. Now, this also assumes that I don't have a rogue DHCP v6 server. If I've got a router that's rogue, I'm probably using the same box for rogue DHCP v6. Wow. So that means the client could just be getting all kinds of weird stuff. But we'll talk about that in just a few minutes. So this was a lot of hunting and pecking. Okay, yeah, we got the packet, we got the trace, live or otherwise, we got a trace. I got a filter, okay, since you've already built your profile and you're building your filters, you got this, you click on it, you minimize it down to all you're seeing just these few router advertisements. We see very quickly something doesn't look good, let's go look in the packets. Whew. That's a lot of work. What if I built a filter, or not a filter, but a profile that gives me a lot of information right off the bat? It gives me, I built columns for my L, A, M, and O flags and my prefix. And I'm looking at just router advertisements. So now I can see really quickly, I got these two routers, the flags that are set, the prefixes are advertising. Oh my goodness, this is not good. Bang. How did I build it? Very carefully. All right? But you saw how quick it was to change the profile that already had everything I needed. Bang. Right? So I'll go back to the January 2017. And let's quickly get to that similar looking stage. All right? I'm gonna build in all 4 of those flags. And I'm gonna do it slightly differently. I want the A flag, then the L flag, then the M flag, then the O flag. Now that I've got a packet open, right-click on the A flag setting and say, apply as column. It will add that column immediately to the left of the info column. All right, and it says autonomous address configuration flag A. Well, that's way too many words. So I'm just going to edit the column and call it A flag. And then I can start sizing this, all right? Again, I've got a packet with everything I need, so let's apply a column with the L flag. Let's apply a column with the M flag, and apply a column with the O flag. And now I'm going to attempt to right-click, edit that column, and let's just call it L flag. And edit that column. Nope, not that. Call this the M flag. I know I'm taking up some time here, but you can see if you spend the time up front or right as you're starting to get into it, you can save yourself a lot of time down the road and make it a little bit easier when you're starting to look at this information. I did it again. And get it to the point of what you want to see. O flag. And now for every other time, it's easy. Now, I also wanted the prefix. And it's down here under the prefix, or the IPv6 option prefix information. I want the prefix and apply as column. And so now I can see all of that information. We can kind of slide these around a little bit, put these back into column number order, and let me reduce this just a little bit. And I can see at a pretty quick glance here, if I look through, a couple things. All right, you know what? Let's just sort this on source addresses. And now I can see there's that rogue. And here's my public, or my production. So it appears that I only have 2 routers, one good, one bad. And this is now in this same profile. Now, if I look at DHCPv6 traffic, just as an example, then I've got all these other columns in here that are helping me. So this is where I would actually go in and make a copy of that profile, give it a different name, router advertisement detail or something like that, and bring it up when I need it. Or I can also come in here to column preferences, and I can deselect these real quick. And then I'm back to my basic regular profile that I had. Here we go. Now, the larger the packets, or larger the traces, the longer it takes for the filters to go through. So sometimes you may have to wait 15, 20, 30 seconds. You know, or again, depending if they're bigger than that. But still, the basic idea is those filters and then those profiles can bring your eyeballs into focus of something very, very quickly. And you may have lots of these. You may have some for your application, doing some testing. You may want to look at other things. I showed the router advertisement with router solicitations a while ago. And it's going to go through and find some of those. There's some pink. Oh, I've got to sort it on the wrong thing. There we go. Yeah, I should have some pinks sporadically in there. Okay, so those router advertisements told us a lot of information. So I am now curious, if I've got 2 routers, what are the chances that I might have 2 DHCPv6 servers? Since both of the router advertisements had the M flag set. Well, if I've got one bad router, what stands to reason next? A bad DHCPv6 server or rogue DHCPv6 server. So two things. I'm just going to go up here and look at DHCPv6 traffic or packets, DHCPv6. Now I've actually got a filter pre-built, but that's fine, I've got this. And let me do a quick little bit more zoom in here. So remember the acronym is SAR, solicit, advertise, request, reply. So SAR, solicit, advertise, request. Whoa. Advertise. And look at these addresses. That advertise, that looks like that's my real router, and that guy is starting to look like that other one. So, oops, I've got a rogue DHCPv6 server to go along with my rogue router. Now here's the best part. I did a request. All the DHCPv6 servers that could reply, replied. Which reply am I going to make my request to? Or which advertise am I going to send my request to? The first one or the last one?
First.
First I heard. It's opposite with routers. Last I heard with routers, first I heard with DHCP. And the biggest problem can become later down the road is, look for a few more solicits in here. Look here, who's my first reply here, or my advertise is the bad guy one. So I'm going to send my request out. It looks like the bad guy one replied here. So the rub now becomes, we have the same up here, when will this client ever get the right addresses? It's all on timing. It's all about timing. If at any point I do a solicit and these two reverse, my real one becomes the first reply I get, I'll use it. So the basic reported problem is, and tying between the router advertisements and these DHCPv6 advertises is, the client or the user is reporting intermittent connectivity. And it's because its addresses are changing from global Unicast to EULA. Back to globals, EULA for a long time, global, EULA global for a long time, EULA. It's intermittent because it's on timing. How often the router advertisements are going out, and then the client says, oh, now here's another component. The clients are supposed to do what they're told based on the router advertisement concerning addressing. I've made that statement. However, just because I get two router advertisements back to back, and one said go do DHCP and the other one says don't do DHCP, does not mean I will actually act on it right that second. For instance, Windows 7 through all of its service packs would make an immediate change. If it just got a DHCPv6 address and 2 seconds later it gets another router advertisement with the M flag off and the A flag on, it will drop that DHCPv6 address and do Slack. But not Mac OS 10.7 and 10.8, and I think up through 10.9. Oh, thank you, router advertisement, for that telling me go do DHCP. Thank you, DHCP server, for an address. That address is good for 2 hours. Cool. 2 seconds later, I get another router advertisement that says no M, but do A. Thank you, but I still got an hour and 58 minutes left on my time. I'm going to keep that address for another hour and 58 minutes. When I'm done and I release that, then I will do Slack. Unless I get another router advertisement within that hour and 58 minutes. So different client operating systems will react differently in the use and adherence of the router advertisements and the timing of their valid addresses that they currently have. This means you have to not only just test V6 communications, you've got to go through all these kinds of things. you have to purposely induce not good things in your V6 test bed to validate what's going to happen with all of your different client operating systems. And when I say all, that includes which service pack levels you're running, which is going to be great because the desktop team will say, we're running Windows 7 Service Pack 1 with the V6 add-on across the board. And I, as a network guy, I'm going to snicker heartily, probably laugh out loud, really, and get hit because I'm not going to believe it.
The reality
I'm not the
is,
desktop guy.
the reality is they'll say everything's current, but then you have all these lab networks that are self-managed that'll be everything and anything.
Agreed, and that becomes the other problem. Your lab environment in this world has to really mimic the production.
But, okay, I got some tools with IPv6 that I'll test all the possible permutations of all the flags that could also possibly done while I'm running real traffic.
You can.
Mm-hmm. That should be part of out-of-the-box testing.
Could be. Say some might not. The real key is this information is not well publicly discussed. It's not that it's secret. Nothing is secret. It's just it's not largely discussed. There's been a couple of books that has been written about where we talked about this stuff on purpose because we discovered it in our own testing.
Sure. It's not hard to write a Python script to do all this.
Oh, yeah. There's a couple of, I call them IPv6 security assessment tools, hacking tools, that you can configure specific packets.
Or just do fuzzy testing.
But it's really the issue of testing on all the different operating systems, whether they're client or embedded or whatever they might be, up into including, the firewall, the routers, I mean, everything, to see what actually occurs when things like this happen. And I look at this and I go, 2 advertises that did kind of confirm what I saw with my routers. Okay, if I see a bad router advertisement, a bad guy router, I'm going to also make an assumption I have a bad guy DHCP v6 server. It doesn't mean I'll find it. It doesn't mean that there is, but I'm going to make that as an initial assumption for me, just because of my experience. And at this stage, I'm going to go, if I've got one bad thing, I'm going to probably have a few bad. Because these exploits are, I would say, effectively well known. There's a really nice white paper that Cisco has, I can't tell you exactly where, but on first hop security, IPv6 first hop security. Because there are a few now capabilities of blocking bad router advertisements. One of the features is called RA Guard, Router Advertisement Guard. The problem is it's really easy to exploit. And about only half the router vendors implement it because of that fact. There are similar things like DHCP v6 spoofing protection, just like there is DHCP spoofing. It helps a little bit. And it's basically where you say what ports you trust router advertisements and what physical ports you trust DHCP v6 packets on, right? And so, but they've got, Cisco's paper is like the best one that talks about these. It's about 5 to 6 features and which code and their stuff. And most of the other enterprise router guys have implemented most of the same feature sets as well. But you have to be a little careful. Sometimes it takes code updates or upgrades even, not just updates. And so then you got to deal with that issue of what does a router code upgrade cost. So with this, one of the quick little things that I found that I build is let's just look at only DHCP v6 servers that are sending out advertise messages in this trace. So I'm just going to go to the advertise, message type advertise, and I'm just going to say apply as a filter, select it. All I want to look at are DHCP v6 advertisements. And as soon as I apply that, and then I start to see these, then I'll do a sort on the source addresses, and then I can very quickly find out, okay, I've got 2. And then, even more fun, I can look at one of the bad guy ones, and let's say, what addresses is it giving out? Well, if its router prefix or network prefix it was giving was the FD01, it would stand to reason that its DHCPV6 server is giving out addresses out of FD01. So the bad guy router has got all bases covered. I'm telling you to get my DHCPV6 addresses, and I'm giving you the prefix for your network, so all your traffic comes to me. All right? It's doing what I would expect it to do. And if I look at a good router, or a good DHCPV6 reply, I see my addresses are coming out of a 2001 DBA. So, again, that is expected. But this starts to explain why this client, why this user, or most likely a VLAN's worth of users are calling in with intermittent connections. Stuff is working and then it doesn't. Oh, it's working again. Oh, it's not working again. It hasn't worked for 5 minutes. Oh, wait, it's worked. Oh, quit again. Oh, it went for 30 minutes just fine. Oh, now quit. All right? I just hope I get it when it's working, close the ticket, done. NTF, right? No trouble found. And then they call again, we open up a ticket. Wait, it looks like it's fixed again. Now, we're going to go look at the packets. And we see why. The why is becoming really, really apparent here. Right? We had a bad router and a bad DHCPV6 server, giving us addresses that are good, that aren't useful. So the basic premise in, I would say, the first bit of V6 troubleshooting is to go look at the router advertisements, see what they're doing, look at DHCP traffic, and see what it's doing. If you're doing DHCPV6. If you're not doing DHCPV6, then it may still be a good thing to go run it though, right? Especially if you got routers sending out with bad flags or misconfigured flags from your network. I'm not going to say that's going to solve anything or it's going to tell you anything, but it's going to knock off a big chunk of the possible not issues. All right? If you can validate that the infrastructure is okay. Now we just got to maybe look somewhere different. Is it an application, or is it a server, or is there something got an address that wasn't supposed to get a DHCP? It wasn't supposed to get a DHCP address, like a server, let's say, and it should have been with a static address. Or we thought we had a reservation for it. A quick little second comment in DHCPV6. In DHCP version 4 addressing, if you configure a reservation, what do the DHCP servers want to use as the key identifier for a client to give it a reserved IP address? The MAC address. That is not the case for DHCPV6. It uses another value called the DUID, the DHCP unique ID. It's a number that's this long. It's bigger than a V6 address. All right? It has generically no relationship to anything on that client. The MAC address, its hardware number, its IP address, its serial number, nothing. It is considered a randomly generated number that's this big. All right? And so what you have to do is find the DUID of that client and put that in the DHCPV6 server reservation field and then say this is the V6 address you want to give it forever. The fun part in the early days of ghost imaging software, after a client is all built up and running, the DUID is self-generated the first time the OS comes up and is locked. And so now you ghost 1,000 computers with that same image, and they had the same DUID. So the first of the 1,000 machines comes online. We build a reservation to an address, let's just say :::3, and that client gets it. The second of the 1,000 machines comes on, and it says, hey, I'd like a DHCPV6 address, and the server says, yeah, oh, do it, Jeff, I know you. You're colon 3. Here. I, being machine number 2, do the DAD test for colon 3, and machine number 1 answers, yeah, that's me, I can't use it. Yo, DHCPV6 server, I need an address. Jeff, yeah. You see where this goes? Apparently that's been fixed in most ghost imaging software, where they take out the DUID, like they strip out, machine name and other stuff now. But that was an early problem of cloning machines, or like in one particular lab scenario where I made about a dozen VM clones. They all had the same MAC address, the same DUID, all kinds of stuff messed up. But anyway, it's just to kind of know this. Hang on half a sec. There's another RFC that's been in discussion to change that, to use the MAC address. There has actually been a field option now in DHCP request messages to pass the MAC address through. However, there are no production-grade DHCP-v6 servers that are using that yet, including Microsoft, including 2016. Because they basically said, there's a system that works, we're not changing. Yes, sir.
DNS mask is using the MAC address.
Say again?
DNS mask, it's commonly used on Linux
Yes,
routers.
yes.
They're using the MAC address.
Yeah, a couple of, there's another Linux one I think will use the Mac as well. But yeah, Microsoft doesn't, it won't.
So based on the comment with the DUID, the DUID identifier, regardless of what interface you go out, it will still give you the same IP address based on the fact that it's only looking at that.
Well,
Assuming that you can reach the DHCP server.
the DUIDs are unique per interface.
Per interface,
Per interface. I'm trying to remember, I think I did that once with like a USB Ethernet and a built-in Ethernet and not DHCP.
Okay.
Pretty sure, but I'm not going to totally guarantee, so you might have to check that.
Test that in the lab.
So, and just a little sidebar in DHCPV6, right, for reservations, having to use the DUID value. You can actually see that if you do a NetSH, interface IPv6, show address. No, show address is equal 3. Nope. Here's DUID. Right here. Now, some OSs are starting to embed the MAC address in the DUID, but it's not a requirement based on the RFCs. But some might. And this is causing a lot of grief in desktop management or device management, trying to track it, because we've been tracking with MAC addresses for years, right? And now in V6 world, we don't necessarily track it by its MAC address for any other particular reason. So just a little tidbit. Okay, I'm winding down on time. What I wanted to do, there was another scenario. So I want to open up that December file, trace file. And I'm going to step through a couple of similar things, but this one has an interesting kind of twist to it. First thing I want to do is look at router advertisements. I see very quickly I've got 2 routers giving me the information. So let's real quickly run up to my handy dandy little filter that shows me what's set and what prefixes, and I can see very quickly a flag on the FE80::5 is not set, and a flag on the other one, which I'm now going to call a rogue, is set. I know this to be not what I have for my production world. My production world is a DHCP world. So the A flag being set means to me it's a rogue router, right off the bat. I also see it's sending out a prefix. Network prefix, 2001 DB8 74C, too bad. Well, that's kind of a giveaway to me, but, too bad may not necessarily have to be bad, but it is bad in my case, all right? So I know this is happening. So one of the things right off the bat, if I see this stuff occurring, I see this address coming out, I wonder how much this network prefix is being used. If I've got router advertisements going out, I should have clients reacting to the A flag set and getting this as a prefix. Make sense? Should, right? Clients do what they're told to do. So I'm going to build a really cool filter. And we talked about this last time as well. Oh, I don't have it in here. Oh, wait, not on that profile. I don't have it here either. All right, cool. We're going to build a filter, and what I want to do is I want to look at the fourth hextet. The fourth hextet was too bad. All right, that's a unique component in the address I can go look for really, really quickly. So I'm going to build this filter called IPv6.source, and then I'm going to say go to the source address and count off 6 bytes and look at the next 2 bytes and see if they equal 2B:AD, too bad. So this goes to the IPv6 source address, counts off 6 bytes into it, looks at the next 2 bytes, which equal the fourth hextet, for too bad. I know it's a little kind of weird looking, but it works. And with that, I want to find every time that that address is being used. And what I can see very quickly is that not only is it being used, but look at all the stuff that's going on. And what's even more interesting, I see pings, I see queries. This is basically regular traffic. This client's trying to do its regular work using a network prefix that's not going to go anywhere outside my world. So this will also equate most likely to the intermittent connectivity problem. Because I'm going out a bunch of places. And I can see, if I also look real quickly at this, there's only 32 packets out of 2,700, and they're all the same address. So it means basically only one host is affected in this trace.
Can you, like, cut and paste that filter into Notepad or something?
Okay, see you now?
Yeah,
Make it bigger.
way
Can
too
you
small.
Make it bigger.
Thank you.
I mean, that's,
Make it bigger.
Cut and paste it into Notepad or something?
we can't see
filter.
anything you're typing in that bar.
That
at all.
filter
Oh, I can't make that bigger up.
I know, that's why we're saying, can you send them to us?
You will get
Okay,
in the PDF these little lab scenarios to go through all these.
okay.
Okay.
Yeah, because I mean, that's about
Yeah,
a
I know.
pixel high from
Here
here.
is
And I'm in the front.
There it is.
Okay, is it, it is square bracket.
Here's what I configured. Go look at the V6 address, source address, go at 6 bytes, look at the next 2 to see if they equal out. That's the display filter that I just configured.
Okay.
That's what's in the little green box that you can't see. But you'll get all these. Now, the next bit I wanted to show in this, what is my official cutoff time? Did I just hit it?
You're about to.
Yeah.
You got 2 minutes.
You have 2
Right about now? All right, real quick. The interesting thing was that in packet 1915, we can see right here, he did a ping request. He's using a bad network, but he's sending a real ping request to a public network, which is actually equal to Google.com. So one question becomes, it looks like he did a DNS query. Did he get a DNS reply? Generically, he probably didn't get a DNS reply because the DNS server is over here at 2001-470, probably doesn't have a route back to this router because it's a bad guy router. All right? So we're making a whole bunch of these legitimate requests, but we didn't get answers back to that V6 address. But remember, if I go look at that guy, I bet he made a V4 request for a quad A record resolve to www.google.com, and I have that, and that's how I can make this ping to that address of www.google.com because I've got that in my local cache. So one of the things that got me thinking about this, well, I just wonder what all this thing is doing, this client is doing, with just only this bad V6 address I see. But what else is it doing? So go down to its source MAC and build a filter, not strictly based on the source MAC, say selected, and I find out, well, this guy is doing all kinds of stuff on V6 and V4, and if we went through and looked down here, we might see in those packets that he made a DNS query on V4 for a quad A, he did, and shortly thereafter he did a ping on V6 that will go nowhere, but he was using a real address. I start thinking about some of this stuff and go, well, does it ever work? The user reported intermittent, right? So two things, filter out V4, all right? Let's go look at the V6 addresses only. Now that I've, oh, wait. Keep this and say V6, whoops, V6. I want to look at this MAC and V6 only traffic. Oh, hang on, I did not get that right. Let me back up. So this, go back. Let's build it this way. There it is. There's the source. And I want to look at that source on any V6 traffic. So apply as filtered and selected. And here is what I find out. I'm also going to do a sort on source address. And I see FE80 linked local traffic of that source MAC. A lot of linked local traffic. Really a lot of linked local. And here's some of the too bad traffic. Oh, and look, here's some of the regular real production address traffic. So this validates the reported problem of intermittent, of sometimes working and sometimes not working, because sometimes it's got a real V6 address, and sometimes it's got a bad V6 address. So now really what I'm going to be thinking of, and why I built that filter with that offset to look at just that Vortex TET, is I would expect a whole VLAN's worth of devices, or any other networks that rogue router may be plugged into, to be giving out bad addresses. So this may be why one whole group of people is calling in saying everything is intermittent, but no other groups are calling in. We've got a rogue router. Somebody plugged in something that they shouldn't have on the network. So again, everything kind of starts at looking at router advertisements, maybe looking at DHCP, making some decision points really quick. If you see any bad addresses, just go start looking for that. If you're not seeing any bad addresses or bad routers giving out incorrect flag settings, then it's probably not at the infrastructure from that aspect. It may be a routing level issue or some other connectivity, but it's probably not bad addressing. So these little mini labs between the last month stepped through some similar kinds of things, and this one kind of went in a little bit deeper. And so we'll try to get that up quickly. So I have well exceeded my time. Thanks for coming in. I hope you find this useful and helpful down the road. At least some point in time you go, what was it that Jeff said?